and welcome to Coffee and Control, the podcast where I find fascinating people from within the world of control and convince them to answer all of my questions. I'm your host, Lucy Hodgins, and in this episode I had the absolute delight of attending the Control 2026 conference in Newcastle. I actually decided fairly last minute to submit an extended abstract for this conference, but I am so glad that I did because I had an absolutely wonderful time. I also brought along my microphones and recorded interviews with as many people as I could. So join me as I discover some fabulous research and meet wonderful people at the Control 2026 conference. Okay, so I am just about to leave for the ACE and UKACC conference, also known as Control 2026. So this is taking place in Newcastle, which, if you don't know UK geography, is a city that is very, very north. I have never been this north in the UK, but current impressions of Newcastle, very good. I went for a lovely run this morning along the River Tyne. That was very, very nice. They have some excellent bridges. Architecture is very lovely. Would recommend Newcastle. So, just a little bit of background to set the scene for how this conference worked. So, Control 2026 is the latest in a series of biannual conferences organised by the UK Automatic Control Council, or UKACC, which is the UK national member organisation of IFAC, or the International Federation of Automatic Control. However, this year things were a little different because the conference was jointly organised by the Automatic Control Engineering, or ACE network, which is headed up by a lovely researcher called Daniel Coker, who we'll hear from later. So the first day of the conference was the ACE Forum, and this was then followed by 2 more days of traditional conference format posters and presentations. So it's probably no surprise that this conference featured a ton of discussion about the role and impact of AI on the field of control, starting from the very first keynote talk, which was super interesting, titled Control Meets AI, Automation, Autonomy and Intelligent Machines.
So my name is Pramod Khargonkar, and I am currently a professor at the University of California in Irvine. And I've been working in the control area for more than 40 years. I've done very theoretical research as well as applications to manufacturing, to electric power grids, and more recently, connection between AI and control.
So could you give an overview of the kind of really interesting talk that you gave this morning?
So I began by going back in history and talking about the work of Norbert Wiener, who is one of the founding figures in our field, and how he was interested in the role of feedback and control and communication in machines as well as in animals. And when you look at his work and what he foresaw, you see very profound thinking on building intelligent machines. Also, a lot of thinking on interdisciplinary work. So, he was a mathematician and certainly control theorist, you can argue, but he brought together people from psychology and from neuroscience and from anthropology and, of course, physics and mathematics. And ideas such as neural networks have their origins in Macy conferences. So I talked about this history and how AI was created at the Dartmouth conference. And one of the things that I didn't get to mention in the talk was the term AI was chosen to distinguish it from cybernetics, which was Wiener's term, because McCarthy didn't want to associate himself with Wiener.
So I just wanted to add a little bit more detail here for anyone less well versed in the history of AI. So the Macy conferences that Pramod mentioned here were a series of conferences on cybernetics that took place between 1946 and 1953, focusing on a wide range of topics closely linked with control, including decision theory, homeostasis, memory, self-regulation, the concept of feed-forward action, and a whole lot more. For anyone interested, you can access the complete transactions from these conferences online. If you would like to learn more about Norbert Wiener in particular, one of the very early episodes of the In Control podcast did a deep dive into his life and work, so I've linked that below if you're interested in listening. Now, the Dartmouth conference was an 8-week-long workshop that took place in the summer of 1956 and is widely considered to be the birthplace of AI. One of the organisers was the computer scientist John McCarthy, who coined the term artificial intelligence. As far as I could tell, Norbert Wiener was not invited to this conference. There's a quote I found from McCarthy about his dislike for the term cybernetics that says, and I quote, "Its association with analogue feedback seemed misguided, and I wish to avoid having either to accept Wiener as a guru or having to argue with him." Basically, McCarthy did not like Wiener.
After introducing this history and connecting control to the concept of intelligent machines, then I talked about the future. And I talked about how cyber-physical systems as a concept provides the natural place for control to make big contributions, and how intelligent machines are being created and will be created in the future by combining machine learning AI with cyber-physical systems. And that's where control is going to interact with AI. So that was sort of the second big point I made. This was followed by concepts of cognitive cyber-physical systems that have cognitive properties like perception, memory, attention, problem solving, etc. And physical AI, which is the next frontier for AI, where AI gets integrated into physical world. From there, I talked a little bit about how robotics is changing as a result of more AI-driven or learning-driven approaches. I followed that up with how humans will interact with intelligent machines, and human-machine collaboration will be a big part of that future. I talked about autonomy and automation and the distinction between the two, and how future intelligent machines will traverse this two-dimensional plane of autonomy and automation, and exactly how we will design these systems so that they serve human needs and human society.
I wanted to quickly clarify this point being made about autonomy versus automation, because it's not automatically obvious what the difference is between these two terms. So automation refers to the extent to which the machine is able to make decisions by itself. So at lower levels, it might require approval from a human, and then at higher levels of automation, the machine might inform the human of what it's doing, or you might have a fully automated system where the human's not necessarily even aware of what actions are being carried out. Technical autonomy refers to the ability of the system to learn and adapt, and it has close ties with the explainability of the system. So the lowest level of this would be a transparent deterministic system where you know exactly what's going on and how decisions are being made. And then at higher levels of autonomy, you have adaptable systems which may also be open to their environment, so able to change in response to external factors. I've linked the original paper that proposes this framework if you would like to understand it in more detail.
And I sort of ended up by talking about safety as a fundamental new field where control can play a big role. So, everybody knows about AI safety, but I think physical AI safety, where we are talking about safety of these intelligent machines that are operating in the real world, whether that's a manufacturing system or a robot or a power grid or whatever thing you can think of, how do we ensure safety? Because that will be the bedrock on which any future development of control and AI working with the physical world will take place. So that kind of is an overview of the talk.
So this technical talk was then followed up by an introduction to the ACE network by Daniel, who I mentioned earlier.
I'm Daniel Koka. I'm a professor at the School of Engineering at Newcastle University. I'm also the PI, director of the Automatic Control Engineering Network.
So could you explain for anyone who's not aware of ACE and what it does, so kind of how did it come about and what role is it trying to do?
I mean, the story of ACE is quite interesting because it's probably in 2020 we were approached by the program manager from EPSRC at the time.
For any younger researchers or folks outside the UK who might not be aware, EPSRC is the Engineering and Physical Sciences Research Council, who are the main funding body for engineering and control-related research within the UK. I actually recorded an episode last year with Andy Lawrence, who's the head of engineering at EPSRC. I'll link that below as he gives a detailed overview of how the grant application process works and also some advice for getting your research funded.
She had one-to-one interviews with academics working in control, and then she convened a group of academics, myself included, It was Will Heath, Alessandro Stolfi, Antonis, Steve Duncan from Oxford. And she said at the time, why don't you actually think about putting together a network? Because she felt that community needed an injection of to believe in ourselves, in control, probably lack of visibility, probably drop in number of applications that identify control as a major, the keyword. So we said yes. And by the time I volunteered to lead the proposal, from the start, we wanted this to be focusing on challenges. So we set it out at the time around the 4 grand challenges that were very visible, and government set them up at the time: AI and data, clean growth, aging society, future mobility. And we said, well, we want control academics and researchers to think what's needed from control community to address these challenges. So that was the ethos. And so now here we are after 3 years and a half. Quite a lot has been done.
So I think here is a good place to introduce another key player who has contributed significantly to a number of initiatives organised by the ACE network.
So I'm Francesca Boam. I'm Associate Professor in Control Systems at UCL. So I'm involved with the ACE network in my role as EDI Chair, and I'm also part of the Executive Board. So I participate to, let's say, the decisions and the organization of some of the events. As a EDI group, we have been initiating some events and initiatives. For example, we have started with the EDI survey. We wanted really to understand what was the situation of our community. It was really, first of all, about understanding the status, the demographics, but also the needs. What is it actually needed? In the past 3 years, it has expanded, and therefore we have now launched a new EDI survey, which is available online from the ACE website. And really we want to understand, to get a bit of feedback on what we have already done, both as EDI group and also together with the early career researchers group. We have been working really together. I think that for me, EDI is really about making sure that everyone can feel belonging to the network, independently from categories. I don't see that. It's more about really everyone being there. So early career researchers are part of the EDI priorities in my sense as well. So yeah, with this new survey, we want to get some feedback on what we have already done, and we want to understand what's missing, what we did well, what we did not so well, what we could get better.
Nice, excellent. Could you explain a bit about the mentorship scheme as well?
Yes, sure. That is another great initiative that we have developed. I'm very proud of it. I think it's quite useful. And what we do is matching people, mentees with mentors, both from industry and academia. It can be students, early career researchers, or early career academics, anyone that feel the need to have a mentor figure to support their career development, or also career changes that might happen. And our role is to try and find a good match based, of course, on the availability and the interest of the people, looking also at specific research interests or specific EDI needs or interests when possible, of course. So it's really supporting and providing a framework for this exchange. And so far we have had quite a lot of interest, but the opportunity is still open if there is anyone who wants to find a mentor. We are supporting that. It is possible to apply through a form which is available on the ACE website as well.
Is this specifically UK focused?
So the ACE network is a UK-based automatic control engineering network, and the target is mainly for UK-based researchers. But of course, some of the initiatives are open also for people from abroad. For example, the ACE Forum and the ACE UKACC Control Conference, we really don't want just to do it for the UK research, but it's a way to exchange, showcase, and of course attract collaborations and opportunities.
So like maybe students in other countries who were wanting to maybe come to the UK would be able to take part in the mentor scheme?
Absolutely, yes. Absolutely, yes, yeah.
I've left a link to both the EDI survey and the mentorship scheme in the description. The EDI survey only takes about 5 minutes to fill out, and I would definitely recommend signing up for the mentorship scheme. I signed up when it first started and got matched with a wonderful academic working in biological control at the University of Warwick, who I have already mined for advice about postdoc applications. Another thing that ACE has been working on is making the case to funding bodies and to the UK government that control is a vital contributor to the UK economy, and that, if anything, the advent of AI is making control even more critical. Here's Daniel again to explain a bit more.
I think that there were a few key outputs that we set up to deliver. One was the a position paper. And I'm not sure if there was ever a paper which set up, or in recent years, which set up a clear case for control being a strategic area for UK to invest in. So the goal was to articulate the need for control, especially at the time when AI seems to be taking over the conversation. So the second one is this research roadmap that we want to publish soon, so that creates a bit of direction for the community. So to articulate what are the priorities, why they are relevant, so in a way help our colleagues align their research and equally align it with the funders, with the government priorities, focus on the outcomes in particular, but at the same time help them prioritize, because there are a lot of things that you can research, and sometimes you may be drawn to something or another, but how do you decide, well, this is something that actually it's going to have a bigger impact? And I think that needs to be considered. So we thought that by articulating this roadmap for the future, we actually help community to rally around a more research program. That because if you all work in our silos and do bits here and there, then maybe combining them, it doesn't really bring something big and important. But if we're coordinating, then we channel our efforts to solve some of the big questions.
One extra thing that hasn't been mentioned yet is that the ACE network has also organised a bunch of events over the past few years for students, academics and industrial engineers within automatic control to meet and interact, as well as online webinars on various interesting topics. They also have a summer school coming up for PhD students, and I will hand over to Francesca to fill you in on the details.
One last initiative that I would like to talk about is also the ACE Summer School that will happen in September. It is open for PhD students and researchers, and it will be a nice mix of technical skills, theoretical skills, but also application, and the themes are around collaboration with industry and within research, and we will focus on control tools that can be useful for everyone to apply on their own research, and we will try to be also hands-on with some challenges that will be presented soon, and some case studies that will be introduced during the school.
If the ACE network sounds like something that you'd be interested in, I have left a link below that you can use to sign up and be kept in the loop about all the exciting events that are taking place. So after this long but hopefully useful diversion into the ACE network, we are now ready to return to the topics of discussion at the ACE Forum on the first day of the Control 2026 conference. So I've just come out of a panel session on kind of recommendations regarding the future of control, I guess, and kind of real world impact of control. So there were a bunch of really interesting discussion points, so things like international collaboration, the importance of input from industry, kind of how we develop skills in graduate students, like training PhD students up kind of with the skills that they need going forward, and also a massive amount of discussion on kind of role of AI, so how control interfaces with AI and consequences of that. One of the things that I found really interesting was there was a question about kind of blurring the lines between AI and control and whether it's important for control to have its own individual identity rather than being kind of a subset of AI or kind of integrated with AI. And the response from the panel was basically saying that kind of AI can be seen as an opportunity to showcase like the capabilities of control. So obviously a lot of control is about ensuring stability of systems, making sure everything is safe. That's kind of something that can contribute to AI. So AI systems are fundamentally just sophisticated models that transform data. So we can basically view this as a kind of model that we can control, which is something that was talked about in the plenary lecture this morning. And then another one of the panel sessions was basically saying like whether control has its own independent identity is maybe not like an important question that we should be asking. It's more like, do we as a community, do like incoming students, like are we having the opportunity to engage with important problems that people actually care about? And if that is the case, then kind of the question of identity will really take care of itself. And there was another question that was asked by one of the audience members on kind of public engagement with control and like the perception of control like by the general public, and basically saying like to some extent the general public are turning against AI systems as being kind of unreliable. And there was mentioned about the kind of recent release of Claude that got shut down within 2 days, and the fact that like again control, like the safety that comes from control really has a role to play in those kind of situations. I think there's going to be more discussion this afternoon and kind of collaborative conversations later on about public engagement, about control. But this is something that I find really interesting as someone who is very passionate about public engagement and outreach. And this is something that I talked about with Brian Douglas as well, is that like traditionally we as a community are not very good at telling our story to the wider world. We tend to just like talk to each other. There's a question of like, how do we convince other technical people? So like in funding committees, how do we convince them that we as control engineers actually have a really important role to play, which obviously is a really important question. And I think that's something that is related, but again, kind of independent from how do we make society aware that control is a fundamental discipline that underpins everything that is going on and is arguably very important in the advent of AI. But yeah, very interesting. It's been a good morning. I've spoken to quite a few people in the coffee break, some of whom I recognise, some of whom I haven't necessarily met before. But yeah, good event so far.
Hi everyone, my name is Chow. I'm from Queen's University Belfast. I'm currently a research fellow. So the topic of my poster is modeling analysis of aircraft service chains using time arc color Petronites.
So a Petronet is a particular approach to modelling distributed systems, and these are composed of transitions, places which loosely represent the system state, and arcs which connect places and transitions together. Also, a little later on, Chow mentioned MILP, which stands for Mixed Integer Linear Programming, so optimization problems where some of the variables being optimized are restricted to be integers.
Well, so why using Petronites? Because for this kind of aircraft maintenance system, normally it should be described as event-driven system, and it should have a discrete state space. Those kind of systems cannot be described as continuous time systems, because in aircraft maintenance, you have the aircraft landing, taking off, the task fixing, finish the task, etc. So we use this Petronite model, and so the main problem here is that the classical optimization or the commercially generated MILP scheduling plan provided by airline company may not be feasible. There may be some conflict between resources and the conflict between several tasks among several aircrafts. So that leads us to this model and use this model to verify whether or not the given plan is feasible. This is the first problem. And second problem is that within this model, we determine whether or not there exists such a plan. That's like a meta problem. So if there exists such a problem, and then we ask aircraft company to provide their scheduling plan, and we then verify it. So that's the basic idea here. We're currently actively engaging with an airline company in Greece called IGIN. So this project is supported by an EU Horizon project called UNIMAS. And I think that's all.
So hi there, I'm Liam Hallinan. I'm a postdoc at the University of Cambridge. So my research looks into analysing the stability of the electricity grid, and particularly what I'm looking at is trying to see if we can derive decentralised stability constraints that can be used to certify plug-and-play interoperability within the grid. So trying to see if we can create grid codes or interconnection standards that different devices must obey in order to connect to the grid. So this has become a very important problem recently. So the grid is currently undergoing a huge, profound transformation. So previously the grid was composed of a small number of synchronous generators, kind of behaved as the backbone of the electricity grid. And that kind of system was always analysed in a very centralised way. So previously the grid operator maintained a huge monolithic model of the grid and performed eigenvalue analysis to determine if it was stable under different scenarios. But now the grid is evolving and it's changing to a more meshed and variable topology with thousands of active participants and new types of devices and control schemes. So that type of centralized approach is no longer scalable really, and we need to try and move towards a system that's as distributed as the grid itself. So that's basically what my work has looked at. So the poster here that I'm presenting is proposing a new stability framework based on applying frequency domain quadratic constraints on local grid subsystems. So what we're able to show is that you can break the grid down into different types of subsystems. So one type of condition that we're imposing is at a bus level. So looking at particular generators or loads and trying to see are there any conditions that we can impose at a bus level that would lead to this kind of plug and play criterion where new devices can be added to or removed from the grid without having to retune all the existing controllers within the network. And then another type of approach that we're proposing is looking at more extended subsystems, so trying to group different parts of the grid together, so grouping buses together with some of their lines that are connected to them or some of the loads that might be local to them, and applying constraints on those types of systems too. So that's basically what this work is about, and what we're able to show is you can mix and match different conditions across different frequency ranges, also different type of system configurations, and trying to make the best of both so that we can create less conservative conditions, derive grid codes that are more scalable and more compatible with new types of devices that are connecting to the grid, like grid forming inverters. So yeah, that's a quick summary of what we're showing here.
So I'm currently walking back from the first day of the conference. The weather is very, very nice, pleasantly warm. For context, whilst I was in Newcastle, the rest of the UK and also parts of Spain and France were experiencing what is possibly the most severe heat wave ever seen. So I was feeling extremely fortunate to be so far north. I've really enjoyed the first day. It's been very nice meeting lots of people. A lot of people who I kind of recognise. Sometimes I don't know if they recognise me, and it's like, do I go and talk to them? Definitely looking forward to tomorrow, the plenary lectures, and hearing about all the different research that's going on. So yes.
Hi, my name is Salma Iraqi and I'm an undergraduate at Lancaster University. So what I'm presenting today is TERA, which stands for Taylor Model Enabled Reachability Analysis. It's a framework that is open source and is available on GitHub as well as all the benchmarks to demonstrate its capabilities. The main motivation for it obviously comes from safety critical systems, where just knowing what happens from one single trajectory is not enough. We need to be able to provide mathematical formal guarantees on the safety of the behavior overall, and this obviously within the control context more applies to safety verification in general, controller validation, collision avoidance, so on and so forth. The main data structure underlying methodology is Taylor models and set-based reachability analysis. Taylor models are attractive as a choice, especially for nonlinear systems, mainly because they combine a high-order polynomial term with a rigorous interval, so you're balancing that approximation while ensuring a validated result. is guaranteed throughout all computations, as opposed to some of the more simpler alternative choices like intervals or zonotopes, which might be faster but get quite conservative much more quickly.
I've added a link to this GitHub in the description if you're interested in checking it out.
In terms of how we've kind of benchmarked it and how we've demonstrated it, while it is still a work in progress, it does work. It's been able to successfully produce results on more than 20 benchmarks across like helicopters, controllers, quadrotors, everything under the sun in terms of the control applications, and it currently provides support to nonlinear continuous systems, hybrid systems with discrete transitions, and then probabilistic reachability for stochastic systems. And the goal is to extend this even further in terms of the scalability side of things. There are still some trade-offs, so it's not fully optimized yet, as well as extend it to support stochastic hybrid systems to support as much of the real-world scenarios as we can. And then, yeah, the current goal is to just take it from here and provide a unified platform that makes it easier to experiment without needing to understand the nitty-gritty of all the mathematics behind it. But
nice. So the first session of the second day of the conference was focusing on theoretical advancements in control. Sadly, I didn't manage to get interviews with any of the speakers, but there were two presentations that I wanted to highlight in particular. So the first was by Anton Selvanov, titled Spillover-Free Boundary Control of PDEs via L2 Residue Separation, which presented a novel approach to controlling partial differential equations that addresses some of the limitations of traditional approaches that use truncation. And Anton ended up winning the award for the Best Early Careers Researcher for this presentation. Another talk in this session that I found super interesting was titled Performance Analysis of Model Predictive Control with Multiple Constraint Horizons, which, as you might expect from the title, analysed nonlinear MPC in cases where multiple constraint horizons are being used, and it provided theoretical design guidelines and trade-offs to help inform implementation. So it's currently lunchtime of the second day of the conference. I was a bit sleepy during the talk this morning, but I just downed a load of coffee and went and looked at some of the posters whilst people were queuing up for lunch, and there are some very, very interesting posters that people are presenting, and I'm really hoping that I will be able to, or that I will get the chance to speak to them about it. Lots of things that either I'm just like generally curious about, or that like I have friends doing PhDs in a similar area, so I want to like go and talk to them and find out what they're doing and how it relates to the work of people that I know. So the plenary session this morning was by Miroslav Kristic. Super interesting. He's an incredibly engaging speaker, and even though my work is like so far removed from the stuff that he does, I was still able to follow like basically the entire presentation, which is massive kudos to him because it's just like a really complicated area. So this talk was titled Feedback Linearization in Infinite Dimensions, from Exact to Machine Learned, and it gave an overview of 4 not yet submitted papers that Miroslav has been working on. So the general idea was looking at how to apply feedback linearization, which is a well-established approach to dealing with nonlinear systems, to hyperbolic PDEs, which are a particular form of partial differential equation. So Miroslav started off by outlining the exact framework, which involved infinite sums, so couldn't be practically implemented. The next part of the talk examined the impact of truncating these sums, and then he moved on to discuss neural operators, which are a particular kind of machine learning architecture designed to learn maps between infinite dimensional spaces. So the third part of his talk was looking at how to learn these operators in the case where the system is known, and then finally he discussed the adaptive case where the PDE parameters are learned online. As well as his talk being really well explained and technically excellent, another thing that I found super interesting was that he mentioned using generative AI tools to improve his workflow in terms of developing theory and proofs, and then using Claude or other tools to check his work and find mistakes. And Miroslav mentioned that this sped things up considerably compared to a similar piece of work that he'd done previously that had completely exhausted both him and his collaborator.
Hello, my name is Mohammed Abdallah. I'm from Loughborough University. I'm a PhD student in the Control Systems Department. And my research today is regarding receding horizon polynomial planning for motorcycles. So the main problem we have with motorcycles is they have a lot of stability issues that are not kind of present in other vehicles. So for example, you need to keep them balanced if you're riding them. And there's not much that's been developed for motorcycles in terms of safety as we have in cars. So one of the things that you could do is like motion planning, which we do have a lot of in vehicles, but not much of in motorcycles. So my research, essentially, this section of my research is trying to focus on developing real-time path planners for motorcycles to make them safe and like kind of usable for people in real time. We are, of course, assuming that there's a rider on this motorcycle, but we are assuming that they're not doing anything, they just sat there. So the second issue that you have is that motorcycle models can be quite big. So in terms of how much computational power you need to make these path planners, it gets very complex. So one big chunk of my research is actually just simplifying it into a reduced order model. That's where the Taylor approximation stuff and all that comes in. But the gist of it is you distill the essential dynamics of the system into a very simple model that you can then use in a very lightweight computational setting. And because it's linearized and everything's very simple, you end up with this convex trajectory optimization formulation. And that is where the backbone of my path planner comes in. It's optimizing for like a certain objective, and you have these certain constraints that it has to meet. So for example, staying within the corridor, or if it has to avoid the obstacle, etc. All those constraints are kind of embedded into the planner. And the idea is we want this to work in real time, so it has to reiterate at every kind of X number of seconds or whatever. And the problem with that is we need to make sure that it remains stable. So we have something that we use in the cost function that's known as a terminal cost that just allows it to go to zero, which basically is how we would test stability in that case. And at the moment, it's still very preliminary. This is the part that I'm working on in real time. So the real-time testing itself is still ongoing, and I need to make sure that I can guarantee that it's stable when it's running in closed loop. So all that testing and everything is still going on. But the long and short of it is hopefully at the end of it, we can come up with path planners for motorcycles that we can use and hopefully improve safety,
Okay, so I am just walking back my hotel after the second day of the conference. So yes, overall today has been really good. I have met a lot of new people, so some really lovely PhD students and undergrad students, kind of conversations about doing a PhD, which was really nice. So this evening there was the UKACC AGM, which was really interesting to sit in on. I was by far the least experienced person there. It was open to everyone, but there were no other PhD students there, so it was a bit of a weird experience. I also said some things. I was like, does everyone now think that I'm really stupid? Yeah, but it was really interesting, and I really like being feeling like I'm a part of that community and making suggestions, and other people are like, yes, this is actually a good suggestion, maybe we'll do that. So yeah, that was really good. I also did a full-length interview with one of the researchers, so Francesca Boehm, that I'm going to release hopefully very soon, and that was absolutely amazing. I loved interviewing her, she's so lovely. So yeah, definitely look out for that interview. There were a few parts of the day where I had to take a minute out because it was a bit overwhelming. I feel poster sessions, just so much noise, so many people, the research is really interesting, the people are really lovely, but sometimes I'm nah, cannot do this, and then just have to take 10 minutes or so, go find a quiet place to sort of decompress. But yes, it's been good. I have my presentation tomorrow, which honestly is a little bit scary. Usually I'm quite chill about presentations, but all the presentations today were extremely technical, and my presentation is not at all technical. And also, because this is a single track conference, the room is massive. Or the presentation that I did at CDC last year, there were maybe 20 people in the room, whereas this lecture theatre, I don't even know how many people it can house, but hopefully it'll be fine. I feel no one is actually there to judge you, they're just genuinely interested in what you're doing.
I'm Luke Rickard. I'm a postdoc at the University of East London, working with Eric Kerrigan at Imperial College London and Paolo Fluggi at the University of East London. So the work I presented today was looking at how we can form coalitions of buildings in order to share energy. So in particular, we have sort of a shift in the way energy is generated from a small number of large-scale power plants to a more distributed energy generation scheme with the introduction of rooftop solar, for example. And we want to see, can we form clusters of buildings we call coalitions that can share energy amongst themselves in order to reduce the amount that everyone is paying for electricity. And this has sort of been studied before in the literature under the notion of coalitional control. We're sort of advancing upon that by looking at how we can still form coalitions whilst keeping a minimum amount of information shared and trying to still get nice results from that with sort of a hope that we can also improve how scalable these algorithms are.
I'm Will Rhodes. I'm a final year PhD student in the control group at the University of Cambridge. I'm also a member of the AgriForward CDT for agricultural robotics. So my PhD is in agricultural robotics. The topic of this talk was on some experiments I've been doing a consensus-based control in the field with real plants. The idea is that currently farmers use precision agriculture to adjust fertilizer inputs for different regions in the field, but we want to do that at the individual plant level because for some specialty crop, you need to really do it at the individual plant level. Neighbouring plants can have a huge amount of variability, and if we can sense the state of a plant and adjust its growth, we can potentially increase yields.
So my name's Dan Hobson, and the research that I'm presenting here today is about control of animatronic systems. So we're talking here about robots primarily for film and television, these sort of things where instead of just trying to get your robot to, for example, be accurate, maybe moving something industrially into a precise location, now we're talking about robots that need to somehow express emotion or sort of communicate with the user, right? This can also be for stuff like if you have human-machine collaboration in a work environment or something, there's places where you need the motion to be expressive, right? And so that's the kind of thing that I'm trying to look at. The traditional way that you do this, particularly animation and animatronics, is you get artists to very carefully craft trajectories, right? You spend weeks and weeks very carefully deciding exactly what sort of motion you'd like so that it looks drunk or shy or, excited or something. And then you try and track that as accurately as possible. And if the robot moves the way that you've described in that reference, then you get this shy or drunk or whatever, right? But this is very labor intensive, right? Every single motion that you possibly could want to do, you now need someone to describe exactly how to do that motion. You're baking in the style, right? That's the thing. And what I'm looking at is that that's not how real biological systems do it. If you look at the neuroscience into how the spinal cord is structured, the spinal cord is what drives motion in humans and other vertebrates. They have small, neural circuits, these little sort of modular components, and those modules are the things that dictate how somebody moves, right? So the way I walk, the way you walk, the way other people walk, comes down to exactly how my learnt neural circuits are different to yours, right? And what this actually looks like in the context of control is that instead of asking an artist to design the reference trajectory, you can ask them to help you design little modules. They design part of the controller, and then once you've got all these small modules, they encode these sort of properties, have a module that is always low frequency dynamics, or a module that's always high frequency dynamics, or whatever you want the stylized motion to look like, you can bake that into the controller, and then whenever you apply a reference, it can be any reference you like, you end up with effectively a filtered control signal, a signal that's projected down onto this subspace that is only the space of moving shyly, or moving like Lucy does, or moving like this other character or something, right? And so we show that you can have the same supposed reference being tracked by two different controllers, and of course those two different controllers stylize the motion in different ways.
So I've known Dan for quite a while, and he is an amazing presenter and one of the winners of the best PhD presentation for this conference. He actually brought in a simple animatronic robotic system that he'd put together to demonstrate what this looked like when implemented on physical systems, which was really cool. Okay, so it is currently lunchtime of the final day of the conference. So this morning there was quite an interesting talk from one of the editors at Wiley, the publishing company, about the use of AI tools in kind of academic publications and also editing. That was very interesting. And then there were presentations on applications and control, including my presentation. So all the other presentations in that session were incredibly interesting. And my presentation, I think, went well. I really enjoy doing it. I feel like I'm always really nervous about presenting. And then after the first sentence or so, I'm like, oh yeah, I kind of know what I'm talking about. So my presentation was on the use of iterative learning control in stroke rehabilitation. And essentially, it was asking the question of like, is iterative learning control the right approach? Do we need more of a kind of feedback type approach? Very quick background on iterative learning control, or ILC. So this is a particular approach to control designed for systems where the same action is carried out repeatedly, and it uses error information from previous trials to update the input at the next trial to gradually achieve convergence to the desired objective. So if you know much about ILC, or iterative learning control, you'll know that generally the assumptions are that there aren't any non-repeating disturbances and that the initial conditions are fixed between each iteration. But when you look at how biological systems and kind of rehabilitation systems work in practice, you see that basically all of those assumptions are violated in a way that actually means that iterative learning control sometimes really struggles to achieve the objective. So this is kind of a discussion of that, trying to highlight some of the challenges that people have maybe overlooked in the past, doing a little bit of theory to look at convergence. So one more session of presentations this afternoon, starting quite soon, and then, yeah, it'll be the end of the conference. The final technical session of the conference was on control in education, and I managed to get to speak to a lovely researcher named Anthony Rossiter, who was talking about some of the tools he's developed to help introduce his students to control concepts in an engaging way.
Okay, so the Control 101 toolbox, the rationale behind this is to help students access MATLAB tools for basically learning control engineering. We found over many, many years that students were struggling with basic MATLAB functions, STEP, TF, etc., struggling to use them effectively. So the point of this toolbox is to create an interface which makes it easier for them to access the tools. So basically the LiveScript environment allows you to write something like a Word document which explains the scenario, and then alongside it a little bit of a code snippet saying, here's how you actually do it on an example. So there's lots of live scripts to do basic control core stuff which students might need. The second aspect of the toolbox is virtual laboratories, trying to get students to understand what is control about, why is feedback important. So we've got lots of virtual laboratories which are things that you can bring into the lecture theatre. So an example I'm showing Lucy here is a tank model. So the whole idea is the students can see a tank on the screen. They can see it filling, they can see it emptying, they can see you change the area, they can see you changing different parameters and how the behaviour is affected. So the whole idea is to bring control concepts into the lecture theatre in a simple, interactive way that students can engage with.
This toolbox is available for free on the MATLAB file exchange. I've left a link in the description, but you can also install it within MATLAB exactly the same way as you would with other toolboxes. Okay, so it's currently the end of the final day of the Control 2026 conference. I'm just about to sit down and edit together the episode. I've really enjoyed this conference. It is the smallest conference I've been to. It's the first conference where there's just been a single track, which has its pros and cons, but I kind of liked it. It was fun being able to present to a large number of people, even though I was really nervous about it going in. And it was also really lovely to get to speak to most of the people that were at the conference. I felt like I got the opportunity to actually talk to, which was really lovely. So on one level, it was really nice to talk to like academics working in control within the UK who I was aware of but had never actually like spoken to. That was really fun. And then also just like networking with PhD students and like undergrad and master's students, talking about their experience doing a PhD and kind of comparing stories and comparing concerns about going forwards with postdocs and stuff. So yeah, it was just like a really, really lovely environment. So, in summary, the ACE Network is a UK-based organisation designed to create community between researchers and engineers working in control. It does this through organising events, setting up mentorship schemes and developing position papers and roadmaps to showcase the excellent work of this community. Control research within the UK covers a broad range of exciting areas, including precision agriculture, path planning for motorcycles, electricity networks, aircraft servicing, animatronics, and much more. And the control community in the UK is incredibly lovely, very welcoming, and you can also be part of this by joining the ACE Network via the link in the description. That's all from this episode. I really hope you've enjoyed it and found it useful. Massive thanks to Kate Kelly and Abelfaz LeVay, who organised the conference and were very supportive of me creating this podcast. As I mentioned earlier, the next episode will be with Francesca Boehm discussing her super interesting work on networked systems and attack detection. That should be released at the start of August, but until then, I hope you have a wonderful month.